So like we started in exponential equations, we had the graphs. Today we're going to look at log graphs and how to find those. A lot of transformations knowledge, again, is what we're going to use. So to start, we need a basic graph, and then we'll learn to move it around and manipulate it. So what I always do when I'm dealing with logs is I remember it's the exponent I'm looking for. So the base is 2, and if I was trying to think, like, what's some good points, right? If this was my graph, you know, I'd probably be talking about, you know, like x equals 0, y equals 1, things like this, you know, like easy choices for my graph. And remember, the log is the inverse of it. It's going to go backwards. So if I want to get good points in the log of log base 2 of x, if this is what I want good points on, then these are going to be my x values. Otherwise, I need a calculator, and they're going to be very difficult to find. So let's make a little table here for x and log base 2 of x. So if 1 is the value, the exponent must have been 0. It's going to go backwards in that table there. If 2 was the value, then 1 must have been the exponent. If 4 was the value, 2 must have been the exponent. If 8 was the value, 3 must have been the exponent. So that's what gives you somewhat of an idea of how to strategically pick points on the log graph, is think about it backwards, pick good points from the exponential graph. Now I do also want to show you how the negatives work. So what I'm going to do is, let's go back to this graph here. What happens if I pick like x equals negative, let's see here, sorry, not negative, but what if x equals 1/2? What's the value of, nope, not a square root, sorry, I was right. If x is negative 1, what's the value for y? In the exponential graph. 1/2, thank you. Yeah. So until you're really comfortable with logs, it helps to just think about exponents first and go backwards. So what if it was negative 2? What would this be? 1/4, yeah. And let's do one more. If it's negative 3, 1/8. So I can add some more values in my table here. You know, it's not obvious that this is a good point, but at 1/2, it would be negative 1 as the exponent. At 1/4, it would be negative 2. At 1/8, it would be negative 3. So that gives me some more points so I can see what's happening with the graph. So the first thing then, if I'm going to start plotting these, x equals 1 is a 0. X equals 2 is 1. And then I got to go all the way out to x equals 4, and I get up to 2. And then I go to 8, and I get up to 3. I'm going to try and do the fractions for you here too. At 1/2, it was negative 1. Then at 1/4, it was negative 2. At 1/8, it was negative 3. So it would keep going like this. And I'll connect the dots for you. This is what the basic log graph looks like. And we're going to learn, like I said today, to figure out how this can be transformed. So let's just look at the basic picture, and then maybe you can tell me a couple of things about it. For example, what does the domain appear to be in that basic picture? It has to be bigger than 0, yeah. It doesn't go across. It doesn't touch the y-axis. It doesn't go past the y-axis. We'll talk about that in a second. What about the range of values? What happens to the range? Yeah, that one, you can see it goes all the way down here. It's very slow, but it is eventually going to cover all real numbers here as well. And there is an asymptote on this graph.
0.
Yeah. Can someone refresh my memory? If we took a basic exponential graph, where do we find the asymptote? You haven't moved it. Where's the asymptote going to be? Yeah, sorry. Yeah, it's going to be at y equals 0 on the exponential graph. So it should make sense to you then when I go to the inverse graph, x and y switch. So now the asymptote's on y equals 0. Sorry. Now the asymptote's on x equals 0, right? Let me write it down just since that was a goof up. Exponential. I'll do it in purple. It's at y equals 0. Normally it would have been here. Now that I'm going to the inverse graph, all the x and y values switch, so the asymptote is also switched. That's why you find it at x equals 0. Okay, hopefully that was clear. What about if we compare this to the original graph, y equals 2 to the x? Then I'll continue in purple, I guess. This one's easier to graph out. At 2, it'll be 4. At 3, it'll be all the way up to 8. And then it'll be a half, a quarter, an eighth, like that. Can anybody give me a real nerdy math description of how you could... That's probably not steep enough. Let me try it better. Anyone give me a description of those, despite my terrible artistic skills? Yeah, so it's this reflection if you have forgotten about it. My graph is a rectangle, not a square, so it's not the best mirror to look at. It's a little distorted. But that's what we think of for inverses, right? They're reflected in the line y equals x. So all those properties you already know from inverses still apply. Let's talk about some peculiarities here. This is something that people... it's not really a struggle, but it helps if you understand why these things are the way they are, because it's a little peculiar if I just give you the work and say, oh yeah, don't forget this applies. So let's try and solve this one here. You get this log base 2 of negative 8 equals x. So what you're really trying to say is 2 to what exponent is negative 8? Right? That's what you're trying to think of, is what exponent can make that happen? What do you think? 3 is 2 to the 3 equal to negative 8? It is impossible, in fact, right? There's an asymptote at 0. That exponential graph never goes anywhere near negative 8. It doesn't go anywhere near the negatives. So one peculiarity about the log graph, and it's because of the way the exponent works, you cannot have the log of a negative value. So that doesn't mean it can't be something like, that you can't put a negative number. Like if we had something like 2 minus x, and I gave you negative 3 for the value of x, that's okay, because if x were equal to negative 3, I'd have the log of 5 here, right? That's okay, but the last end result, before you hit log in your calculator, before everything is done, it has to be a positive number, right? It cannot be negative, because that would be a way of saying, oh, if you take a positive base and you raise it to an exponent, a magically negative number comes out, and you can't do that. If the base is positive, every exponent is going to be positive as well. Okay, so must take a positive value or argument. So some of you might be thinking, well, but what if you changed it, Mr. Joyce? It would work if you went, what about negative 2 to the x equals negative 8? Haha! Now it works, right? What's the value of x in this case? 3. It works. However, there are some significant problems with this. Can anyone think of, yeah? X has to be an odd number. Yes, it's even worse than that, because, for example, if I did something like 2 to the 1/2, that again is not something that we're prepared to deal with yet, right? That's an imaginary number, a complex number. So it gets really bad when we have a negative base. So in logarithms, if we want to make it defined, it's not properly defined for a negative base. There's all kinds of problems. In fact, there's infinitely many problems with a negative base. So for a log, the base must be also positive. You get too many problems with negative bases. Leo's suggestion, of course, was that like if I said negative 2 to the x equals negative 16, that doesn't work now because x would have to be 4, and that would make it a positive 16. So if you didn't catch on to what he was saying could go wrong, that's another problem. So that's it. We're done. There are too many problems. Logs are always a positive base. Okay, then the last thing about the bases for logs. Well, I guess we should think about this. Can the base be a 0 or a 1? Like, for example, is it possible that I go like... yeah, you happy with that? Yeah. There's no problems with the exponent. But what happens when I flip it is kind of strange. Because here I could say x equals 0, x equals 1, 2, 3. It works for so many different x's. If you remember the horizontal line test, that means there's too many points. It's not going to be a function when I go to its inverse. That means the log is not a function for this. Here's the picture. This is 1 to the x. Right? Now if I reflect it along the line y equals x, here's the log graph that will come out of it. What does this mean? It means log can't decide because it's not a function. If you're trying to say, what exponent did you use, you're always wrong. Because you might say, oh, look, Mr. Joyce, you used 1 squared equals 1. That's the answer, right? And I go, no, that wasn't it. And someone says, oh, I know, it was 1 cubed. And I go, no, that wasn't it. And we can play this game forever, and you're always wrong because I can just pick a different number. Any number works. The log can't tell you what exponent was used because every single number works. So because there isn't one answer, you can't do this with a log. And the same rule applies to 0, right? If you had 0 to any exponent, your picture looks just about the same, except it's a flat line here. That's 0 to the x. And that means we'll do it in orange. This would be the log graph you get here, which again doesn't work. You try to tell me what exponent did you use, Mr. Joyce? There's so many answers that I can always make you wrong. It's not gonna give us the right answer. So no, base cannot be a 0 or 1. It's not a function if we do that. So those are some of the peculiarities that come up. Basically what happens is when we're practicing and reviewing or doing your homework, you go, hey, why did I get this question wrong? Or I don't understand why the answer in the back of the book is like this. It's probably because you forgot one of those little details about logs. All right, so now let's transform that graph that you just met. Quick review here. This is our VSF. I mean, by now you probably don't need this, but it is also a Monday morning, and it's, not a bad thing to review. So this is left and right. And this is the up and down. So if I actually turn this into the log graph, this is where the parts go on the log graph. So now you have the vertical stretch factor in front, and you have the horizontal stretch factor there, and you have your left or right, and you have your up or down there. So I wouldn't try any new tricks or shortcuts. I would simply say, think about what the base graph would be, and then let's transform those points. So can anybody suggest some good x values if we were to just look at the base graph? And in this case, the base graph would be y equals log base 2 of x. What points would you want to use that would give you some nice values? Yeah. Which is the base graph? Good question. The base graph means you take out all the transformations. So you don't move it left or right, you don't move it up or down, you don't do any kind of transformation there, and you don't do that reflection there. So the only thing you're left with is a log 2 of x. Right? You take all the pieces that moved it out. So if we're in log base 2 of x, what's a good x value, right? You want to be able to pick nice exponents, so what's a good x value? 2 is a good x value. The exponent would be 1. Okay, what's another good x value? 4 is a good x value. The exponent would be 2. What else? 8, sure. Someone give me a fraction. 1/2, yeah, 1/2 works. Exponent would be -1. Okay, give me one more point. Give me a fraction. 1/4, sure, why not? So now when I'm going to transform these points, I'm going to have to think about what I've got here. I've got my reflections, expansions, compressions, and any translations. I'll just move this over so I've got some room. So let's take a look at this graph here that we started with. Are there any reflections in that graph? Yes, there are. Is it an x or y axis reflection? Good. So that means the y coordinate on all these are going to get flipped. So I'm going to have 2, -1, 4, -2, 8, -3, 1/2, 1, 1/4, 2. Okay, so reflection's done. How about expansions or compressions? Are there any on this graph to deal with? Horizontal, and how much? Good. So that'll be 1, -1, 2, -2, 4, -3, 1/4, 1, and 1/8, 2. And then finally we have to do translations, right? So left, right, up, down. What's going to happen? 3 left, up 1. Perfect. Okay, so that means I'm going to go left 3 puts this at -2. Up 1 puts it at 0. Left 3 would be -1. Up 1 would be -1. Then 4 would become 1. And -3 would be -2. This one's going to be trickier. I'm only using it to graph, so unless you have your calculator handy, there's nothing wrong with just saying I'm going to go to 1/4 and then I'm going to subtract 3. Then I'll move 3 back on my graph. And then I'm going to go to 2. And here I would be at 1/8, and I'm going to subtract 3, and I'm going to be at 1 higher, which is 3. All right, so let's plot these points so we can see what the new graph looks like. I know the anticipation is just killing you. So -2, 0, -1, -1. 1, -2. And then I've got 1/4, and I have to take 3 away. So 1/4 is going to be right near the edge there. 1, 2, 3. It's going to be somewhere back here. And it says that I'm at 2 high. So oops, I'm on this side of the graph then. So it'll be like this. And let's see here. 1/8 minus 3 is going to be very close to it. So it's going to look like that. And if you're not satisfied with the log graph, you can pick some new points. There's nothing to stop you from saying, if you want a point further out, that you could do that. But roughly this graph is going to do this. It's going to be out here. And this is the log, what the log graph's going to look like. And my asymptote's going to be right there. Remember, it's a vertical asymptote for logs. This one's going to keep going lower. It just starts doing so very, very slowly because the log is chopping it down so much. So if we think about from this picture, what's the domain and range going to be? What do you see as the domain here? X greater than. Can anybody see what the value is there? Might help if you look at the equation. Yeah, it's got to be greater than -3. If you didn't know that, how could you predict it from looking at this equation right here? It's been shifted 3 to the left. So it started life at x equals 0. It's now 3 to the left at x is -3. So the asymptote there is at x equals -3. Remember what we said here, though? We said logs can't take a negative value. They have to be positive. That's the problem with if x starts to be less than -3, like if I try to put in x equals -5, that's a problem, because now I have -2, and it's going to be a negative value. So that basically marks the fence that says this value, x plus 3, must be greater than 0 to work inside a log. So x must be greater than -3 to do that. So looking at the equation, you can also do it algebraically if you can't find it from the picture. Whatever's in these brackets here, whatever's in this part of it, always must be greater than 0. Okay. And the range of values is a really boring question. It's going to be all real numbers. I don't know of any log graphs. Maybe there's one out there, but I don't know of any where it's not all real numbers. So here's a problem for you then to think about. We have this, the thing is, how do you graph different logs in your calculator if you only have 2 log buttons? Last day I told you about the natural log and the common log. Those are the only 2 buttons on your calculator, unless you have one of those fancy new ones that you can change all the, I think it's called a right view, or anyways. If you're not lucky like that to have a fancy calculator, I want to show you how to do this. So grab your TI-83s. Okay, so let's just, I'm going to walk you through this process here. We're going to go log 27, and we're going to divide it by the log of 3. Now, what base are these logarithms in that I'm choosing right now? Yeah, they're in base 10. And somehow I end up with a nice number like 3. So we'll think about this. We'll look for a pattern in a minute. What about log of 49 divided by the log of 7? Turns out that's 2. Anybody feeling brave enough to make a prediction? What's the log of 625 going to be divided by log of 5? Okay, let's see if you're right. Yeah, it's 4. So what's actually happening in these examples, to show you how it works in your calculator, is that you've actually, by rewriting it like this, it's the same thing as the log in base 3 of 27. This is the same thing as the log in base 7 of 49. This is the same thing as the log in base 5 of 625. So for the change of base rule, this is what it looks like. You can take any 2 numbers, right? Like log base 3 of 27 in our case, the first one. So if this was 3 and this was 27, what happens is the base goes to the bottom of the fraction, and the argument here, the 27, goes to the top. And you get to pick any base you want. Notice that C just shows up. Anything you like. You can change it to base 4, base 9, natural log, anyone you want. And then you'll be able to get an expression that we can use for graphing in the calculator or evaluating in the calculator. Okay? So that one's pretty important here. Try and evaluate this now in your calculator, log base 5 of 30. See if you can apply the change of base rule. Okay, so you can pick any base you want. So for this one, I'll do log in base 10. And the base goes to the bottom, and that argument goes to the top of the fraction. So you should end up with 2.11 as your value. And again, what does this magic mean? It means 5 to that exponent should be 30, and it is. Okay, so it's finding that decimal answer for you. Now, the next one I'm going to do natural log, just to show you you can pick anything you want. So the base is 3.5, the argument is 10, so it'll go natural log of 10 divided by the natural log of 3.5. So the base is 3.5, argument is 10, it's 1.84. Okay. And here I'll show you, I used a different log, but that's the way it works. It's nice. I can pick any log I want. It's 10. Right? The log you choose doesn't matter. It's what's most convenient for you. What's convenient with the calculator is common log or natural log. So what we should do then is we'll go and take a look at the one we just graphed, and that way we can verify when you're doing your work and you want to check your answer, this will show you now how to graph. So this is the log that I want to show you a picture of, but I don't have a base 2 on my calculator, so I'm going to need to go negative log of 2x plus 3. And in order to get into base 2, I'm going to have to divide this whole thing by log base 2. So what I did here is I've just changed this into log base 10. So the one I'm actually putting in is y1 negative log base 2. Sorry, negative log of 2x plus 3, and it's going to be divided by log of 2. They're both the same, only now I'm able to use the log button on the calculator so I can actually double check my work. So, you know, we know the asymptote's at negative 3, so you probably don't need to go any further to the left, so I'll do something like that. Now my scale, if I remember that picture, it gets quite tall, but it's not very, it didn't come down that far. So let's try like negative 8, and it'll probably be something like 20. This should give me a decent picture of that log graph. And it's not that the, thank you, I'll restart later. It's not that that graph stops there, it's just that this really wicked awesome calculator doesn't have enough resolution to show you the pixels going any further. If you want to see it going higher up, you'd have to change your window to zoom in. So I'll show you with the zoom in here. Let's just go from, say, negative 4. I got to get closer to the asymptote to show it to you. And it still doesn't have enough resolution. Oh well. But anyway, that's why you're seeing it chopped off here, is that the calculator is ancient. I've been at this school for, this is my 8th year, and we were using your TI-83s back then. So imagine what your cell phone looked like 8 years ago, right? That's how cutting edge the TI-83 has become. Wait, you guys didn't even have cell phones 8 years ago, right? No. Yeah. Okay, so now we're going to take a look at what equation we could be dealing with for this log here. So I'm going to give us a chance to think about it and brainstorm how we could do this one. Actually, I'll write this one down for you. The simplification that we made was we said every graph that was like a c to the b x. There was so much stuff here. We said we could simplify every one of those graphs to the form that looked like this. And then we said 2 points will do it. Now that you're here, 2 points will do it. We'd find the asymptote first, and then we'd use 2 points to solve it. The same rules are going to apply here. Find your asymptote first, and then think of 2 good points. Okay? If this was the exponent, what's the log graph going to be? So any log graph, what would it look like? Remember last day we talked about how you can change from exponential to log form. Okay, so that's a lot to think about. I'm going to let you guys take a few minutes to work this out and see if you can come up with an equation. Okay, so let's give this one a try then. If we start with that hint, and it's not something you'll be expected to do obviously on a regular basis because you can use the result. So x minus k is a c to the y. And then because I have this thing in the front, it's going to be x minus k all over a is c to the y. So log base c of, I'm going to write it like transformation style, 1 over a. My pen is sticking together. Let me. And this is just some constant here. I don't know what that constant is. It might be a half, it might be a quarter. So I can actually rewrite that just as y equals log base c of a x minus k. I don't need to write that as a fraction. I can just put it in directly. Okay, so let's figure out what's the asymptote here going to be. That was our starting point for exponentials. We'll do the same with logs. Here's the visual of that asymptote. That happens at x equals 1. So that means here the value of that asymptote is k equals 1. Right? The asymptote will happen when this equals to 0. So when x minus that equals, in this case a 1. No. When that equals 0, and I have x equals 1, so 1 minus k has to be equal to 0. That's why k equals to 1. You don't, obviously, I would just look at the picture and pull the asymptote off of the picture, but that's the algebra if you didn't have the picture in front of you. Okay, so I'm just going to clear a bit of space because I'm running out of room. So our equation looks like this now. Log base c of a x minus 1. And we need a couple of good points to figure the rest of this out. So what can we have for good points here? Yeah, there's one here which is 2 and 4. Okay, what else do you see as a good point? Yeah, 4 and 6 have a good point. So let's try those and see what we can come up with here. If I use those values for x and y, I'm going to get two things. The first thing looks like this. 6 equals the log. I don't know what my base is. And I have this so 4 minus 1 is going to be 3. And then the other one that I'm going to get out of it is from the other point, 4 equals log base c of 2a's. It's getting a little crammed in here. Try and move this over. Okay, so we're going to try the same strategy, which was to write them as a fraction. So if I have 6 over 4, that's the same thing as log base c of 3a and log base c of 2a. Oh, and I'm sorry, that should just be an a, right? My apologies. If I put in x equals 2, 2 minus 1 would just be an a. So the piece that I have then, 3 halves, I'm going to use the change of base rule backwards here because I have the same base. See that base right there? It's the same one. So I can actually toss it. It's going to be 3 halves. The bottom will be the base, log base a of 3a's. And what I get then is a to the 3 halves equals 3a. So if we take one, divide both sides by a, that means I'm going to have a to the half is 3. So a equals 9, because I'll square both sides then to get it out of there. So a is a 9. I can go back up and then use that information to figure out what the value for c is. I'm sorry about how crammed in this is getting, but if I put it back in here, 4 equals log base c, and we just said the value of a is a 9. So that means c to the 4 is 9. So c is 9 to the 1 over 4, which is root 3. Okay, so I could rewrite that as y equals the log in base root 3 of an a is 9 times x minus 1. And just with the exponential graphs, it is possible that you rewrite this in a different format. We'll need some more tricks with logarithms to learn how to do that, but we can go and verify that it does work in the graphing calculator. So you may have a different equation if you do it and you check your work against the textbooks. But let's plug it in here. So that would be the log of 9x minus 1, and I have to divide it by log root 3. And maybe I can see a pretty decent window has already been given to me, so I'll just use the one that's in that picture. The maximum in that case was 10. Oops, sorry, the maximum was 10. The scale was 1. And minimum looks like about negative 12. And we'd be fine if we went as high as 10. So let's just see that our pictures match up. They do in fact match up. The asymptote there is disappearing. You can check with, if you want to trace over points, that's what that blue button there, trace, does. Now you get a cursor, you can walk through them. So we knew that 2 was a good point. We can check, cross our fingers, whoops, and hope that it lines up. It looks like pretty close, 1.95. Yeah, okay, so it would have gone through 4. The other way, have I shown you guys how to do the table? We talked about this, didn't we? Okay, so if we go to table, it's handy because you can evaluate the at several places. You can evaluate your function, cy1. So if you wanted to confirm, you could put in x equals 2. The reason I'm getting errors here is because those aren't defined, right? The asymptote is at 1. So right now it's locked and I can't do anything with it. You need to go second function, table settings. That's table set right there. So you go table settings, and I always leave it set up this way. Is I take the independent variable and I say ask me for that value. Don't just calculate them automatically. That way when I'm on the table, it'll wait for me to enter it. I'll say what's the value at x equals 2? And it says 4. What's the value at x equals 4? And it says 6. So you can double check it as well if the graph isn't a good picture for you to see. Okay. Now, as far as log graphs go, we're going to be more interested in predicting the asymptotes and the domain. So if this was the case, and we dealt with this equation here, what do you think the asymptote would be? Yeah, it's going to happen at x equals 3. How did you know that? Yeah, I've shifted it 3 to the right. Right? So it used to be at 0. It's shifted 3 to the right. The other way I'd like you to think about it is whatever's in here must be greater than 0. That means the asymptote will happen right at 0. That's the border between everything greater than 0 and 0. So how do I come up with the domain? Well, I just sort of gave it away. Everything in there has to be greater than 0. So everything inside that would have to be greater than 3. That's all permissible values that can be used in the logarithm. So I know the asymptote's at 3, and the domain is everything greater than 3. Okay, so how about this one here? Can you predict what's the asymptote going to be? Negative 2 over 3, I heard. Does that sound right? Okay, I'll believe you. And the domain is going to be everything where this is greater than 0. So I'm looking for where 3x plus 2 is greater than 0. So 3x is greater than negative 2. X is greater than negative 2 over 3. So it's everywhere bigger than the asymptote. Be careful when you work with inequalities. Do you remember what you have to do when you multiply or divide negatives? You have to flip, right? Less than becomes greater, greater than becomes less. So if you do come across a question where you divide by a negative or multiply by a negative, be careful. That means you'll have to switch the inequality to make it true. So try it again on this last one here. See if you can come up with the asymptote and the domain. So asymptote is where it equals 0, because everybody on one side's okay, but it can't equal 0 or anything less than the 0. So that's going to happen at, yeah, x equals 2. And then to figure out which side of the asymptote I'm on, 2 minus x has to be positive. So if you did it this way and you went negative x is greater than negative 2, and then you divided everybody, this is what I was talking about. You have to flip it, so it'd be x is less than 2. Now, how do you double check this and make sure that you're on the right track with it? Try a value. If x is less than 2, that means I can put in a value like 0. 2 minus 0, yeah, that's positive. I can put in a value like negative 100. 2 minus negative 100, that's 102, right? Because I end up adding them. So I am on the right side. I can use huge negative numbers here because when you put a negative in there, a negative negative gets added. So this is okay, we're on the right side. If you were careless, you might not be on the right side. It might be worth just double checking 1 or 2 points to make sure you did your inequality right. Okay, so we'll take a look at an application here, and we probably have to get a calculator going to help us answer this one. Shield welders wear, well, that should probably say like a mask or a visor to protect their eyes. Oh, the shield welders, there we go. It's not a shield welder. The shield welders wear to protect their eyes comes with a shade number that can be modeled by this relationship here. Where T is the fraction of visible light entering through. What percentage of light passes through if you use a number 12 to do arc welding? Okay, so that means we're going to try and reverse this equation here. We've got a 12 for the number and negative 7 log T of 3 plus 1. So what we want to do is we want to figure out what's the value for T, the fraction of light that passes through an arc welder's shield. All right, so the first thing, of course, I'm going to make this 11 is negative 7 log T over 3. And I'll keep rearranging this, trying to get the log all by itself. So I'm going to have 33 over negative 7 is the log of T. What base is this in? It doesn't say.
10.
Yeah, good. When it doesn't say that's the common log, we always assume it's log base 10. So I'm going to rewrite this expression then. 10 to the 33 over negative 7 is the percentage of light that gets through. So now I just need my calculator to tell me that. So 10 to the negative 33 over 7. And the answer is not very much. 1.93 times 10 to the negative 5. All right. So we are going to continue working with logs for several days, and historically this is one where students want extra review time, and we are banking on needing more time to review logs. But I'll assume that coming up for your quiz that exponents is okay still. I otherwise need to hear from you between now and tomorrow when we do that. Okay?